very sharp transitions from one geometry to the other. Here's an example of a plate that had the width W, then it goes to the width H, and the fillet radius is R. Here is the stress concentration factor K plotted as a function of R over H. R is this radius, and H is the smaller width of the geometry. And you can see that there are different curves of W over H, where W is the width, large width, and H is the small width. So you don't want to have like a sharp, abrupt transition from one geometry to the other. That's how you minimize the stress concentration. You can see here that asymptotically it approaches 1 of average stress, and you can see that here it goes to 2.5. So if we're not using the safety factor of 2.5, and it's very rare to use a safety factor of 2.5, the part is going to fail in the presence of a flaw. Does everybody understand that? So whenever you do the design, you want to make this radius as large as possible. You want to make this transition as smooth as possible. And if it can be avoided, try to avoid it. Okay, this is the main fundamental difference between brittle and ductile materials. What happens ahead of the crack tip? So you drop a glass bottle on the floor, or you take a piece of glass with a crack, or there is a crack in the windshield of a car, and you're driving the car, and the stone hits it, and the crack propagates. The car windshield is actually a triplex glass. It has a polymer layer in between. But you all had experience with fracture of glass, correct? It's without warning. It's called brittle fracture. And the reason is because the crack just propagates. Whereas in a ductile material, it forms a plastic zone ahead of the crack tip. And that plastic zone, that plastic deformation, stops the crack from propagating further for a moment. Okay? This is called crack blunting. And the crack gets blunt depending on the nature of the material. Okay, let us have a look at the crack propagation criteria. And this was originally done by Griffith. And Griffith published his original work in Philosophical Magazine. Don't get confused by the name Philosophical Magazine. If you want to publish about fracture, that's the top journal to publish. But other countries like China, Poland, Kazakhstan, they read the name of the journal, Philosophical Magazine. What is the magazine about? Philosophy? Well, it's about fracture. And if you are in the field, you know that Philosophical Magazine is the one that you want to publish anything that has to do with fracture. Let's have a look at this. The critical stress, or the stress of the crack tip, is equal to the square root 2e gamma sub s over pi a. Let's look at the terms here. E is the elastic modulus of the material. Gamma sub s is the surface. So imagine when you're forming a crack, the crack propagates, and essentially you have two surfaces, and each surface has surface energy associated with it. Okay? You are creating new surfaces, so you're putting in the work to create the surface. That's why there's a number 2 here, because there are two surfaces. A is a crack length, pi is just a pi. Now, this class, mechanics of fracture mechanics, is spending half a semester on this. And then there are modifications to this to account for plastic deformation ahead of the crack tip. And the way it is done is that this gamma sub s has another term, gamma sub b, which is huge compared to gamma sub s. because the surface energy term is very small. The plastic deformation term is huge. And then it depends if you talk to a metallurgist versus a ceramist. My PhD thesis was in adhesion of thin films. And in my defense committee, I had Robert Cook. And Robert Cook is a ceramist. And he wiped my ass with all this because he cared about this brittle fracture. I didn't care about brittle fracture because my films were copper, and the adhesion was improved by plastic deformation. It's like orders of magnitude difference between fracture in metals versus fracture in ceramics. This is fracture in brittle materials. And the condition for fracture is when the stress exceeds that value. Also, I can tell you that this surface energy is affected by the environment. So if you're driving a car and it's raining and the stone hits, there's more chance that the crack will propagate than if it's dry. My PhD advisor, Bill Gerber, was one of the fathers of fracture mechanics in the United States when they did this after the Second World War and in the 60s. They were putting India ink into the crack tip to outline the crack tip, and they found that this lowers the threshold for the crack propagation. Okay, yeah, I told you we ran out of letters, so KC is called fracture toughness, and it has very weird dimensions. This is the measure of the resistance to the crack propagation of a given material. Look at this equation, okay? It's equal to the stress in pascals times the square root of pi A. Well, A is the crack length. So if you look at the dimensions, we have megapascals times the square root of a meter. It's the weirdest dimensions I have ever seen, and you have ever seen in your life, okay? But this is how it works. You have you have a piece of paper. Okay, you see this? This is cardboard. I'm going to start over here. And you can see that there's already a flaw. In fact, every time you try to open a box like this, what happens? You rip it. You have to be very careful not to rip it, correct? You're all familiar with what I'm talking about. So, what I'm doing here is I'm applying the stress, and there's a flaw, okay? And I'm applying the stress and nothing happens. And then I keep increasing that stress. And at the point when the crack starts to propagate at a given stress level, it just happened now. It becomes at a specific, it happens at a specific combination of the crack length and the stress that is applied. And when that happens, this becomes C, a critical value. That's what C stands for. Y is a dimensionless parameter that has to do with the geometry. And for planar geometries, it's close to 1. We don't discuss it, but actually there are 3 modes of fracture. There's mode 1 like this. There's mode 2, shear like that. And mode 3 is twist. And as you can imagine, I have this shirt example. See, I have a shirt. Imagine I rip it like this. Actually, I can do that. The first, this button is going to go, this button is going to go, right? The first button is going to go. Then the second button is going to go. Then the third one. And then if I pull hard enough, I'll rip it further. You see that? Can you imagine it? Okay. Okay, imagine I'm doing this. I'm shearing it like that. So all of the buttons, all of the shirt is still on me, and it's contributing to this load bearing. So the amount of energy that you would spend to shear a crack is much larger than you would open. Anyway, tech electric next semester if you want. Plane strain fracture toughness. There's a difference between plane strain and plane stress, and again, it takes another course that I teach to explain what that means. But I can tell you, and that's what saved the space race, is that if you take, the book does not explicitly, I'm going to tell you, if you take a thin material, like aluminum, and you try to test it, the fracture toughness of aluminum when it is thin is going to be about 20% higher than when it is thick. And it's a difference of the boundary conditions, plane stress versus plane strain. So just remember that. The material that's thicker is going to have 20% less toughness than the thin one. Okay, these are the values. And you can see that for metals, they're pretty high. Can go up to 100 megapascals per meter. For ceramics, they're very low, up to 10 megapascals per meter. And composites and polymers are also low. You can rip them relatively easily. Does everybody understand this formula? Just remember this. I can apply stress intensity factor, that's another name for it, for fracture toughness. And the crack is not going to propagate. It's not propagating. I'm applying stress, but it's not propagating. The moment it starts to propagate, right there, the combination of that crack length and the stress that I applied is specific to the material, to this paper, to the glass, to the metal, all that good stuff. Glass is around 1. Okay, so if you look at this, there are two ways of designing against fracture. The crack growth condition would be when the K1C is less than. So K1C is a material property that you can measure, that you can look up in the materials tables. There are two scenarios. One when you can measure the flaw, and the one that you cannot measure the flaw. Okay, so in scenario 1, the crack length is specified, and that dictates your maximum design. So you can solve for the stress at which this crack is going to propagate. So if we plot the stress versus crack length, this is a condition for fracture, this is a condition for no fracture. And let's say you have a fuselage of a plane, or you have a wing of a plane. Each plane wing undergoes ultrasound testing to make sure that the defect size is less than the critical value. Okay? K1C and stress levels are specified, then that would give you the maximum allowable flaw size. So you can take this equation and solve it for either A or for either sigma, either for stress or for the crack length. So we can plot the crack length versus stress, and then this is a condition for fracture, and here we have no fracture. And then there's Weibull statistics that's applied. I remember when I was a grad student, we did a lab in ceramics course where we've taken glass rods, and some of them were flame annealed, some of them were scratched with sandpaper, and some of them were tested as received. And each lab, students went in and they tested it in 3-point bending and measured the load at which they fractured. And when I worked at Motorola, Motorola makes a power amplifier. It's a chip about 2 millimeters by 2 millimeters. It's gallium arsenide. Gallium arsenide wafer, 4 inches. I don't know how much it is, but it's like $1,000 for wafer versus $10 for silicon. But each cell phone that you have has a power amplifier, 6 transistors. There's 25 microns of gold on each side. Sometimes it goes kaput. And it's still amazing to me that it, back in the day, it was sold for $2 a piece. Can you imagine that's the scale of the economy? When you have a wafer, you can calculate how many pieces of chips you're going to have on that wafer. So the project was to improve somehow this fracture prediction, and we had an indentation device that would test a whole bunch of those chips and measure the load at which they would fracture and analyze the statistics. So you can either measure the stress at which parts fail, or you can either measure the crack length or the defect size that you would put in this equation. Does everybody understand? Okay, aircraft wing. Aircraft component is made from material that has fracture toughness of 26 megapascals per meter. It has been determined that fracture results at a stress of 112 megapascals. They measured it with a maximum critical internal crack length of 9 millimeters, almost a centimeter, pretty big. For the same component and alloy, calculate the stress level at which fracture will occur for a critical crack length of 4 millimeters. Okay, so at 112, it failed when it was 9 millimeters. When it's 4, what stress level do you expect it to fail at? Higher or lower? Think. You reduce the flaw size. So what would happen to the stress? Crack, stress. This is a constant value. We reduce this, and what's going to happen to the stress? How would it go down if we reduce this? The product of this and this. The stress would go up. The stress that the part can support would go up. Right? Okay. So the first step is to determine this geometrical factor, because it can be important sometimes. And we reverse this to solve for this y, and we get 1.38. So now what we do is we plug this back in here, and we get 168 megapascal. This geometrical factor depends on how the crack is loaded. I can tell you that the best paper is a published paper. This paper is called Bonded Composite Repair Structure Multiple Side Damage Analysis. Like if you have a fuselage of a plane that has cracks, it can be repaired. The problem was that the student who made these calculations, he did it for fixed geometry. It was very hard to publish it because mathematically this problem has been solved in Fortran in the 70s. And you have two collinear cracks, which is a complication compared to what I'm telling you now. And this is a one crack solution. You see this? It's the Y factor here is 1.18, something like that, this blue data. And then for the twin cracks, it varies. This is the geometry. So he made a mistake in his calculations, and over here it was 1, and the reviewers pointed that out, so we fixed the model. This is before the repair, this is after the repair. And what you do is you basically take a patch of fiberglass and epoxy and just fix it up. Gee, this is like, rings a bell or resonates with you? Yes, no? The concept is relatively simple. If you apply enough load, which is stress, there's no material that can withstand gigapascals of stress, like tens of gigapascals. It's going to fail. Even diamond. You can crush diamond. You just apply enough force. The way this is changing is in the presence of a flaw. So that's a combination of the crack length and the stress. But it's funny how we ran out of letters, so The same thing, the same letter K is used for the stress concentration factor, K. It's sometimes called stress intensity factor. It's the ratio of the maximum stress to the remotely applied stress. And Kc is the critical fracture toughness, which has the units of megapascal square root of a meter. I mean, we did everything to confuse the public and the students by using the same letter. Okay, brittle fracture. Everybody familiar with Titanic? Tim Fakey, a student of Bill Gerber, my PhD advisor at the University of Minnesota, is working at NIST, or was working at NIST, on fracture of Titanic when they pulled it up. And the design of the ship was such that if one part of the ship got water, it all sunk. So the further ships that were built later were compartmentalized. If there's a hole in one part of the ship, it doesn't cause the whole ship to go down. The next experience with the ships are Liberty ships from the Second World War. There's one in the port of Tampa. If you ever go there for an exhibit, they have a museum there. I have seen that ship many times living on a cruise, but I actually have not gone to visit. Maybe it would be a good idea to visit the Liberty ship. Those ships were built so fast that they used welding instead of riveting. And welding provides a continuous path for the crack, whereas rivet, the crack would go from one rivet to the other and stop. What people also did not know is what's called ductile to brittle transition. There's a very simple crude test called the Sharpie impact test. And this is the sample geometry. There's a notch and there's a hammer. You take a hammer to a certain height and you let go. And when it swings, it breaks the sample. And depending on how much energy is spent in fracture, it goes to the final height, which is measured here by a dial. It's a very crude, simple geometrical thing, but it works. And if you look at this impact energy identifies the transition. This is temperature. Here you see high strength materials, which are intrinsically brittle, almost like glass. And here you have FCC ductile materials. And BCC and some polymers have what's called a brittle to ductile transition, or a ductile to brittle transition. So the temperature in whenever this was a brand new ship that was deployed. The next morning we cracked in half. We didn't know about this. So there was this oil pipe in China from the 70s. I was on sabbatical back in 2010 there. And Ling Menbing was an exchange student from Taiwan. Back in the day, Taiwan and China were at better relationships than they have now. So they sent people back and forth, and he was a summer student there. This is the pipe. You can see a person standing there. Actually, anytime you show anything like this, you need to put a scale bar. But you can see this is a lab, this is some piece of equipment, so it's huge. This was a spiral welded pipe. So they took this piece of metal, they bent it, and the weld goes around the spiral. And this pipe failed. It was transporting oil long distance. It was underground. You can see it corroded some. And what we've done here, this is the rolling direction. We cut out the samples perpendicular and parallel to the rolling direction. You see, this is the schematic of those Sharpie specimens. And this is the weld, the idea of the weld, that you put enough material there so it doesn't fail. It failed right next to it. Here you can see has heat affected zone, and here is the impact energy. You see 10 or 12 joules versus 40 joules. That was the difference between fracture along the rolling direction versus perpendicular to the rolling direction. Talk about anisotropy, highly anisotropic material. It turns out that during the rolling they introduced inclusions, so it was not a good process, and over time this pipe failed. It was in the service since the 70s, and it failed in 2008 or so. But here's an example for you of the use of the Sharpie impact test. How is this measured? Well, exactly the same way. You take a sample, you put it in liquid nitrogen, boom, you measure the impact energy, then you do it at room temperature, then you heat the sample, stuff like that. We observed a similar effect in thin films. So here's a paper called a brittle to ductile transition in thin films. And I was amazed how Bill would just take the data and fit a model to the data and write equations like this, which at the time I didn't quite understand, but by the time I started to understand these equations, I said, okay, it's time to graduate. They're not so hard, actually, if you actually go through it. Okay, fatigue. Fatigue is whenever you take something and you repeatedly load for a long period of time, like a CV joint on a Nissan Sentra, eventually fails. Or a small car. Anybody had a CV joint fail? Okay, what did you do?
Just replace the whole axle.
You replaced the whole axle.
I mean, you could just do the boot, but I don't have the tools for that, so I just did the whole axle.
You did the whole axle, okay. You did it yourself?
Yeah.
How long did it take?
An hour.
Wow, you're good. You're a mechanic. Or handy. And you have the tools. How many miles were on that car?
Like 120,000.
120,000. Normally, if a car is driven, normally you get 10,000 miles per year, so the car was at least 12 years old, right? How old was the car?
It's 12, yeah, 12 years old.
Okay. So, why does it happen? Why the new car does not have a CV boot failure?
It's not fatigue.
Right, it's fatigue. There's no fatigue. So fatigue has to do with the number of cycles. And you have to realize that when you're driving your car, the axle, the wheels turn, right? And that eventually transports to how fast you're going, right? And then you have the engine with certain RPM, and you have the gearbox and all that good stuff. So every time the axle rotates, it goes. So if I look here, I'm loading it from the top like this, but over one rotation, I'm loading like this. So it goes tension, compression, tension, compression. It's just like taking a paper clip and bending it back and forth like this. But you do it millions of times because the wheels turn. So here's a machine. Here's a specimen. And there's a load that's applied to this And the key parameters are S, sigma sub m, and the cycling frequency. And I will tell you what those parameters mean. Now the maximum stress is way, way less than the yield stress, because we are already taking care of that in the design. And S is the stress amplitude. And N is the number of cycles to failure. So these are actually called SN curves. And certain materials have what's called a fatigue limit. A fatigue limit is the stress at which there is no fatigue. You see here, this is a million, this is 10 million, and so forth, 10 to the 9 cycles. So if you are applying a lot of stress, and we're look at it in terms of the stress amplitude, because it goes tension, compression, with each revolution, right? You can see that there's almost like a straight line, but then it hits the limit. This is the fatigue limit. Certain materials do not have fatigue limit. Aluminum, it does not matter. If you have a part made out of aluminum and you subject it to cyclic loading, it is going to fail regardless of what the stress amplitude is, unfortunately. Right? So fatigue life, N sub F, is the total number of cycles to failure. And that CV boot failed after 120,000 miles. You can calculate 120,000 miles, how many revolutions, how many cycles that was. It's not so hard to calculate. In fact, just ask Google. If the car has 120,000 miles on it, I want to know. How many revolutions of the wheel or the axle was there? I want to know the answer. Can you please tell me? Ask Google. If the car has 120,000 miles, how many rotations wheel took, or axle took, however you phrase it in English? The bottom line is that, like for steel, there's a fatigue limit, and for aluminum, there's not. How can we improve the fatigue life? Is there an answer? 75 million? 85 million. 85 million. So this is 10 million. This is 100 million. So right here, somewhere here, and it still failed. We can improve the fatigue life by reducing the magnitude of the average stress, the mean stress. So don't load it; it's not going to fail, kind of thing. So if you have like a car and you're driving all of your kids to school every day, like 5 people every day, the chances are going to be higher than that's going to happen than if you're driving yourself. This is the stress amplitude versus the number of cycles. And this is the near zero of compressive stress. This is moderate tensile, and this is larger tensile. What I need to tell you is that cracks only propagate in tension. Cracks do not propagate in compression. So even if I take this and I compress it, you don't see me tearing this piece of paper, do you? Do you? I'm pushing on it. I mean, I have other effects of bending and whatnot, but if I compress a crack is healing when you're compressing it. Crack only propagates when you're putting it in tension. Okay? So the decreasing mean stress increases fatigue life. Another one is the surface treatment. if we can put the surface of the material in compression versus tension, then it will improve the fatigue life. How? You can take balls, steel balls, and you can put it in the ball mill, and you can shoot those balls at the surface, bam, 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 bam. It's like shooting, literally, those balls at the surface of your metal. And every time there's impact of this ball with the surface, it makes an indent. And obviously it happens on a very large scale. A lot of those balls, this is called shot pinning. You're mechanically damaging the surface to put it in compression, and if the surface is in compression, cracks do not propagate. The other way is carburizing. Kind of similar to what we've seen through diffusion in that gear, but we can put a carbon-rich gas and put the surface in compression through material science principles to control the process, to control the structure, to control the properties. Process is shot peening or carburization, carburizing. Microstructure is the skin layer that's in compression. Properties improve fatigue life. Design. This is bad design, this is better design. A smoother transition from one geometry to the other. Never make abrupt changes like this. Why? Because of the stress concentration. Go back here, and you're going to see that the sharper the transition, the higher the stress concentration. R over H, R. So we need to increase R to get over here versus here. And who is the designer? Who's going to be the designer? You. So please keep this in mind. No sharp corners, no sharp transitions. Also, external defects, where do they happen? Surface, scratches, mishandling, right? What are the odds of having a defect inside? Pretty small. It has to be a processing error of some sort. But this can be scuffed, surfaces can be scratched. Surface itself is already a defect. Any questions about fatigue? Another failure mechanism is called creep. And creep is associated with high temperature. And the way it works is we take a sample, we put dead weight on it, and we heat up the sample. So creep is associated with high temperature deformation. Roughly more than 40% of the melting temperature. And if we look at the creep strain for deformation versus time, there are three regions: primary, secondary, and tertiary creep. You can see that the secondary creep, there's a linear relationship between strain and time. You take a sample, you put dead weight on it, dead load, and you heat it up, and you wait how long it is going to fail eventually. And you measure how much it sags. This is the effect of the temperature, and if we are below 40% of the melting temperature, you can see that there's elastic deformation and there is no creep. We increase the temperature and the part fails much faster. So you can see that for the steady state creep, you can see it by this dashed line here. It increases with the temperature and with the stress. Both have similar effects, either increase the stress or increase the temperature. Okay, steady state creep is governed or fitted with an equation. It is equal to stress to a certain power times the exponent. exp is e to this power minus q sub c over RT. Q sub c is the activation energy for creep, which is a materials parameter, and is the stress exponent, which is also a materials parameter. And here is the data for the stress versus creep rate. And the notation is epsilon with a dot. What are the units of strain? Meters per meter, so dimensionless. Okay. And then, if I plot this strain as a function of time, or I take a derivative of the strain with a function as a function of time, what would be the units of the strain rate? And the strain rate is how fast I'm deforming it. So I can do it very slowly, or I can do it very fast. This is when I externally apply the strain. But in this case, what we do is we put a dead weight, and then we heat this thing up, and it sags by itself. So we're measuring the material response to creep, and the units are 1 per second. It's per second, because it's strain, which has no units, per unit of time, and the epsilon is the strain. Or it can be measured, as you see here, as a percent per 1,000 hours. Well, same idea. Okay, and you already know the trick. We can make predictions for failure. You cannot take that Chinese pipe and test it for 50 years. It's impossible. Okay? So what we do is we do accelerated test using the Larson-Miller parameter m. T times C plus log of T is equal to m. T is the temperature, C is a constant, T is the time to failure, and m is the function of the applied stress. So we load a lot, we heat it up, and it fails, and we can extrapolate what time it would take for the part to fail at a lower temperature. Is vintage clothes popular these days? Are you guys buying shit at Salvation Army and Goodwill? Why? Oh, that's the only reason? So it's not a matter of fashion. Because I was going to say, I can take new clothes and I can make it old very fast. There are ways to age things. So that's the main reason is the price. If you buy something new, how long does it last? Like you buy a t-shirt, but you don't really care how good or bad it works, like a painting t-shirt. How long would it last? What's the oldest shirt you have? 5 years? 6 years? Anybody? This shirt, I bought in Arizona, like 22 years ago. Still here. So the reason you're buying the clothing from a Goodwill is because it's cheap. But the other reason is because it still exists, right? The t-shirt that you're gonna buy now may not last you 20 years, or whatever, however long. But bottom line is that the same thing with materials. You can do an accelerated test at higher stress level or at a higher temperature. Okay, so this is the prediction of failure. So estimate the rupture of S590 iron at 800 degrees C, and the stress is 20,000 psi. This is the plot of log stress versus Larsen-Miller parameter. Stress in psi versus M times 10 to the 3 Kelvin hours. Okay, so we convert. Please remember to convert Celsius to Kelvin. This is the number one mistake everybody makes. So 800 degrees Celsius is 1073 Kelvin. And we write that T times C log T, small t, is equal to M. So we have 1073 Kelvin times 20 plus log of T is equal to the 24 10 to the 3. So at 20,000 psi, we can see that the Miller parameter here is 24,000. And then we solve for T, and that's going to give us 233 hours of service. It's very important to make this prediction. Okay, we talked about failure, we talked about fracture, simple cracks, fatigue, creep. Any questions? This is again, if you put in an effort to understand it up front, it's not so bad. We're going to talk about composition and temperature. And we want to know how many phases are there at any given temperature. If you look at water, how many phases can water be in? Which are solid, liquid, and gas. And what controls whether water in one of those different phase states? Yeah, what controls it? Temperature, and one more parameter that we always forget. Pressure. This is why when you go up in the mountains, water doesn't boil at 100 degrees. And that's why you cannot use that for disinfection, because it's lower. It's like 90 degrees or less. Water boils when there is less pressure, atmospheric pressure. Okay, here's phase A, here's phase B. This is nickel and copper. It's still nickel and copper, but the arrangement of the atoms in phase A and phase B is different. Since vinyl came back to Walmart and it's popular, anybody has vinyl record player? You do? Okay. Do you know A side and B side? Back in the day, you had to flip the record to listen to more music on the other side, which is called B. But obviously, they would put the best stuff on the A side, right? Does it make sense? So there's the same B side, meaning back on the back. The same thing for the phases. A is the primary phase, B is the secondary phase. So please keep that in mind for the notation. In equilibrium, there's a solubility limit. You like sugar in your drinks? No? Yes? Sometimes? if you add sugar or salt to water, at a certain point what's going to happen is that sugar will not dissolve anymore. You'll see the crystals on the bottom of your glass. But if you heat it up, you can dissolve more sugar. So solution could be solid solution, liquid or gas solution, or it could be a single phase. And mixtures when you have more than one phase. So here you see water and sugar. And this is the composition in weight percent sugar. If you are below 60%, you have a very sweet drink. And this is room temperature. But if you go to 65% sugar, you're going to start to see the crystals precipitate on the bottom of your glass. And if you heat it up to boiling temperature of water, 100 degrees, you can dissolve 80% sugar. So all that sugar that is here at 65 weight percent at room temperature is going to get dissolved. And in this region you have liquid and solid. Liquid water and the sugar. And here you have the syrup. So this is one phase, this is a two-phase region. So the question is, what is the maximum concentration when you only have one single phase of the solution? Or what is the solubility of sugar at 20 degrees? We go over here and we see that it's 65%. And if we're below 65%, you could have sweet water. If we are above 65%, we're going to have sweet water and crystals of sugar floating, and you can actually see it with your eye. Does this make any sense to you so far? You guys get it? Okay. So let's then differentiate components and the phases. Components are the elements or compounds that are present in the alloy, like aluminum and copper. We're forming aluminum copper alloy. But the phases are chemically distinct regions of the material of a certain form, like alpha and beta phase. So here's aluminum copper alloy. If you look at the microstructure, and I hated that they didn't give you the scale here, but it's probably like on the micron level. We have alpha phase, which is darker, and we have beta phase, which is lighter. And it's still, again, aluminum and copper, but they have different compositions. So the amount of aluminum and amount of copper in each phase is different, just like it's shown schematically here. You can see that roughly you have like 50-50 nickel copper, and over here you have more nickel than copper. So these are atomic reconstructions that happen within the structure inside at the atomic level, but they can grow and propagate to relatively large sizes. The temperature effect on the composition. Here you can see this water sugar thing. We can start with this composition, 70%. We can take a precipitated solution, right, of 70% sugar at room temperature and heat it up. And over here, we're going to have only one phase, which is the solution of sugar and water. If we want to change the number of phases in that boiling water or close to boiling water, we can add more sugar. We keep adding more sugar, and what happens is sugar precipitates. And we have two phases. We have liquid syrup and we have sugar. Any questions about this concept? Okay. For solids, let's consider the criteria for solubility. Like nickel and copper. Its crystal structure, both are FCC. Electronegativity, it's very close. It's the radius, also very close. Hume-Rothery rules. Do you remember we discussed Hume-Rothery rules? So in fact, there's 100% solubility of nickel and copper, just like water and alcohol. They're totally soluble because of these three parameters: crystal structure, electronegativity, and the size. This is a phase diagram. A phase diagram typically plots temperature on the vertical scale and composition on the horizontal scale. It can tell you what phases you're going to see in thermodynamic equilibrium. So, a couple of things I want to point out. This is weight percent nickel. So at 0 here, what is the material? Copper nickel alloy, and nickel is 0. What is it? It's copper. And at 100% nickel, what is it? It's nickel. And in between, copper nickel alloy. Okay, so what you see here is something very interesting. What is this 1100 degrees C? What's the physical meaning of that? We had solid here and we have liquid here. What is that called? It's the melting temperature. Okay? Now, please take a look at this. This is the melting temperature of nickel, pure nickel. And this is what? 1450, whatever it is, right? So on the phase diagram, on the two sides, or whatever, you have the melting temperature of a pure metal, in this case copper and nickel. And then in between, that's where magic happens. To control the process, to control the structure, to control the properties. This is the shit. Okay? This is the whole class so far, really. I mean, it's going to get a little bit more elaborate, but I want you to get it now. And what you see here is that there's a region of solid solution. And what you see here is that this white region here has two phases, liquid and alpha. Alpha is this alpha solid solution. And as you can see here, as you are increasing the composition, the concentration of nickel, what happens to the melting temperature of the alloy? Goes up. So you have control through the composition. You're affecting the melting temperature of the alloy. See that? Okay. For binary system, okay, we have temperature, we have the number of components C, and we have the pressure. In binary system, we just have two components. That's why it's called binary. Independent variables are C and P and T. And that is when the pressure is fixed at 1 atmosphere. Any questions about this? Yeah? You are combining melting points of a shitload of alloys. Okay? So, I mean, obviously they're not going to do every data point, but they will do this alloy, then we'll do this alloy. Some graduate student would do this elaborate work, because you need to have a colorimeter to do it. You need to formulate the alloy, you need to melt those materials, right? Then you have to heat it up until it melts, and then that's how this is experimental data. This is why for the phase diagrams, ASM and ASME, they sell those phase diagram books for thousands of dollars, because it was very labor intensive to get this data. You know? That's why it has so much value. Okay, this is called isomorphous binary phase diagram. And this is copper-nickel system. Binary because there are two components. And isomorphous, this is a scientific fancy way to say that there's complete solubility of one component in the other. Just like alcohol and water. You can have 100% water, you can have 100% alcohol, you can have 100% copper, 100% nickel. So if I ask you, what effect does nickel have on the properties of the alloy, what does it do, adding nickel to copper? Look at this. What does it do with the melting temperature? It increases. In this particular system. Because we're going to look at other types where it is actually the opposite, which is very cool. All right. So what we can do is we can calculate the number of phases. Rule number 1. These are the rules. If we know T and C0, then we know which phases are present at each temperature. So this is initial composition. Guys, please remember that if you have $5 in your pocket at the beginning of the class, you're going to have $5 in your pocket in the end of the class. Now, in the meantime, I may borrow you $5, or I can give you $1,000. You know? Can you make an analogy with $5? You came to this class with $5. You're leaving this class with $5. This is important for you to understand because there's magic that's happening in between. We start with this percentage, okay? And this is the percentage of copper, nickel, whatever it is, 35%. And we end up, so in liquid it's going to be 35%. In solid it's going to be 35%. But the way it happens in between, the composition is changing dynamically. And it's following the solidus line or the liquidus line. That's the Latin words for the solidus line. This is the solidus line. This is the liquidus line. At 1,000 and 1,100 degrees C, here, how many phases do we have for 60% nickel? How many phases are here in this blue region? Just one, and it's solid. It's solid solution. And at the point B, which is right here, how many phases do we have? Which are liquid and this solid. And if we are somewhere over here, it's all liquid. Rule number 2. If we know temperature and the initial composition, we can find out the composition of each phase using the lever rule. Okay? Let's say we are taking 35% nickel alloy. At 1320 degrees C, at the point A, what phases do we have? Just the liquid. And what's the composition? 35% nickel. We drop the temperature down to 1190. Point D. What do we have here? How many phases? Right here. How much did you have in your pocket when you came to this lecture? $5. And you're living with $5. So you started with 35% nickel. You ended up with 35% nickel. There's conservation of mass, energy, and $5 in your pocket. But let's consider this point, point B, at 1250. How many phases are present? Which are liquid and solid. The composition is determined by the tie line. A tie line is just a horizontal line. Okay, so we draw, for this point, we draw a horizontal line. And the composition of the liquid phase, this is the composition of the liquid phase, is 32% nickel. And the composition of the solid phase is 43% nickel. Is that magic or what? Is this alchemistry? Can somebody explain to me how this is possible? How does solidification happen? The last time you had a party and you didn't have ice and you put ice in your fridge and people come and you have, was not enough time. What do you have there in those ice cube trays? Half ice, half water. It takes time, correct? Okay. How does solidification happen? It happens over time. It happens through nucleation and growth. Right? We've talked about it. Nucleation and growth. So you need to have a nucleus. And what happens is this nucleus is 43% nickel. It has higher nickel concentration. So those nickel atoms start to get together and they solidify in small nuclei. And we calculated the equilibrium size of those nuclei about 10 nanometers or so. And at the expense of the liquid. So the atoms of nickel go towards the solid phase. That's why there's less nickel than 35%. And it's dynamically going down, boom, 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 until we hit this point, where we start with 35, we end up with 35. If you get it now, it is awesome. Because this is where the confusion comes from. This is the largest confusion in this whole class, and I only have like 4 minutes to start explaining it. Because these percentages are deceiving. These percentages are deceiving because the composition is measured in percentage. And then the amounts of phases is also measured in percentage. Let me explain. The composition of a phase is the percentage of nickel in copper. You get that? Okay. Then, how much liquid is there and how much solid is there? This is a totally different quantity. Okay? Because what happens is this stuff solidifies, atoms are consumed from the liquid, and they become solid. And it happens dynamically. It's like your ice turning into water. It takes time for it to happen. Right? And initially you have more water, in the end you have more ice. And in the end it's all ice. So I don't have the time to go into the details. We will on Thursday. But for now, I want you to remember that there are two percentages. Two different things. One is the composition of each individual phase in terms of the components A and B, nickel and copper. Okay, so 35% nickel. That's the composition of the phase. And the other percentage, which I did not discuss yet, is how much liquid there is, how much solid there is. Do you get it? Okay, so with that thought, keep it in mind, and we'll continue on Thursday.